topics: Newton's laws of motion, collisions, conservation of linear momentum, and frictional forces. Introduction. From the knowledge of the effects of force on a body, unbalanced forces may cause a change in state of a given body. Otherwise, if no external force acts on a given body, the body should remain in its state. In this topic, we shall study the laws governing bodies when an external force is applied. Newton's first law of motion. It states that a body continues to be in its state of Newton's first law of motion. It states that a body continues to be in its state of rest or uniform motion in a straight line unless it is acted upon by an external force. That's law of inertia. Play the video below to observe how bodies obey this law. Inertia. Inertia is a term used to describe the reluctance of a body to start moving if at rest or to stop moving when in motion. Click on the play button of the video below and make your observations. Momentum. The term momentum refers to the product of the mass of a body and its velocity. This implies that a body at rest has zero momentum.
Click on the play button of the animation below to observe this. Newton's second law of motion. It states that the rate of change of momentum is directly proportional to the resultant force producing the change, and it takes place in the direction of the force. Click on the buttons provided and make your observations.
Impulse. Impulse is defined as a force multiplied by the amount of time it acts over. That is, impulse Ft is equal to final momentum mv minus initial momentum mu. That is, Ft is equal to mv minus mu. An impulsive force acts within a very short period of time. Play the animation below to observe what an impulsive force can do. Newton's third law of motion. And this states that if a body exerts a force on another body, the second body exerts an equal and opposite force on the first one. That is, action and reaction forces are equal and opposite. Play the animation below to observe this. Observation. As the air oozes out, the balloon is seen moving in the opposite direction. Discussion. The balloon is forced to move in the opposite direction as a result of the action force the air moves out with, the recoil velocity. When a bullet is fired by a gun, it moves in a certain direction while the gun moves in the opposite with a certain velocity. The velocity with which the gun moves backwards is known as the recoil velocity. The animation below demonstrates this. Click on the play button and see what happens.
Collisions. In this subtopic, we will discuss two types of collisions, namely elastic and inelastic collisions. Click on the play button to observe elastic collision and inelastic collisions. Elastic collisions. When a collision is perfectly elastic, both kinetic energy and momentum are conserved. In this type of collision, when the two bodies collide, they rebound with their initial velocities reversed, showing that both their momentum and kinetic energy are conserved. Explanation. In this case, when the first body hits the second body, that is, which is stationary, it transfers some of its kinetic energy, causing them to move with different velocities. This is an example of a perfect elastic collision where both the momentum and kinetic energy of the system are conserved. In these collisions, the colliding bodies separate after collision. Play the animation below to observe this. Inelastic collisions. These are collisions where the colliding bodies stick together and move with a common velocity after collision. In such collisions, only momentum is conserved as some of the kinetic energy is lost in form of heat and sound. The following animation shows what happens to the velocity of the bodies during inelastic collisions. Click on the play button and make your observations. Explanation. In this case, the dart has some momentum and it transfers some of its kinetic energy to the block during collision, making the two to stick together and move with a common reduced velocity. This example shows that the momentum of the system is conserved, but the kinetic energy is not conserved during the collision. Law of conservation of linear momentum. From the animations on elastic and inelastic collisions, when two or more bodies act upon one another, their total momentum remains constant provided that no external forces act upon them. This implies that the total initial momentum of the system is equal to its total final momentum. This is known as the law of conservation of momentum. Click on the play button of the animation below to observe this.
Friction. In this section, we will look at friction in solids and fluid friction.
Friction in solids. Friction is a force that exists between two bodies in contact and are in relative motion. This force can cause wear and tear as well as fire. Frictional forces can be used in sharpening a slasher. Play the following video to observe this. When the grinder gets in contact with the edge of the slasher during rotation, the frictional force between the grinder and the slasher edge wears off the slasher edge, making it sharper. When the tires or shoes are new, the treads are well defined. After some time, the treads get worn out due to friction, making them to become smooth. When the matchstick strikes the rough edge of the matchbox, the friction between fluid friction and viscosity. When a body moves through fluid, it experiences a resistive or frictional force known as viscosity. In the following animation, we shall demonstrate the behavior of three similar ball bearings falling through three different fluids, that is, air, water, and glycerin. Play the animation below and make your observations. Observation. The ball in a more viscous fluid falls slower due to a high frictional force. Discussion. When a body starts from rest and falls through a fluid, it accelerates uniformly at first due to the unbalanced forces of its weight, upthrust, and viscosity. As the ball speeds up, the viscous drag increases up to a time where the total upward force equals to the total downward forces. At this point, the body continues to fall at a steady velocity known as terminal velocity. The value of terminal velocity depends on the viscosity of the fluid, the shape of the object, and its density.